Yeah, good afternoon, everyone. So we'll start the class. In today's class, we are going to see uh, the first concept. The second concept in first unit, that is lexical analysis, right? As you all know, lexical analysis is the first phase of the compiler design process. So in this class, we are going to learn what is lexical analysis, and moreover, we'll be focusing on how to design the lexical analyzer. Okay, lexical analyzer is the component which does lexical analysis. Okay, so we will see the theory behind lexical analyzer design. Okay, so that is the motto of this lecture, right? So let us get into the content, right? So first we look into the role of the lexical analyzer in the entire compiler design process. In the entire compilation, what is the role of lexical analyzer? So as you can see here in the slide, the lexical analyzer, as I told you earlier, it's the first phase of the compiler design process, which takes input from the source program. Okay, the source program written in some high level language. Okay, so what it does, it will try to identify the individual building blocks of the source program and try to pass them to the next phase of the compiler design process. The next phase of the compiler design process is nothing but the parser, right? So the lexical analyzer will act as a producer, okay, which produces the tokens or the input, okay, required for the parser. Okay, parser is nothing but syntax analyzer. Okay, the other name for lexical analyzer is scanner. Okay, generally we use these two terms interchangeably throughout the course. Like whenever I say scanner, it is nothing but lexical analyzer. Whenever I say parser, it is nothing but syntax analyzer. Okay, so you can see the whole thing. I mean, this entire thing as a producer-consumer problem, where the lexical analyzer produce stream of tokens. Okay, and the parser is going to consume those stream of tokens. Okay, the duty of the lexical analyzer is to identify the tokens and pass them to the next phase. Okay, the functionality of the parser is to identify the structure, to validate the structure of those stream of tokens. Okay, so both of these phases, they interact with the symbol table. Why? Because whenever a new symbol appears in the lexical analysis process, that new symbol is going to be stored in the symbol table data structure. Okay, okay, that information may be required in the next phases of the compilation process. That is the reason why we are maintaining a data structure called symbol table. Okay, as in when you encounter a new symbol in your source program, the information related to that particular symbol must be stored somewhere. Okay, right? So we have the flexibility in high level languages that we can define our own variables. Okay, so whenever you define a new variable, that new variable may contain attributes like its value, its location. It may be an alias to an existing variable. Okay, at some point of the program, you may change the value of that particular variable. Okay, all these information must be stored somewhere. Okay, otherwise the compilation process could be very difficult for us. Okay, so what happens is, suppose if you want to assign this variable to some other variable, if such is the case, what do you have to do? You need to know the type of this variable and the type of the variable that you want to be assign the value of this variable to that variable. If the types are same, if the types are matched, then only we can assign. Okay, like in semantic analysis, when you're looking for type compatibility errors, this information is very much required. Okay, so that is the reason why in the lexical analyzer, the lexical analysis process, whenever we identify a new symbol, that new symbol is going to be stored in the symbol table for further reference, right? So when it comes to the role of lexical analyzer, we can see the main role of the lexical analyzer is to identify the tokens and pass them to the parser. Okay, right? But there is a small problem here. The problem is that if the lexical analyzer produces the stream of tokens very quickly, then the parser is not able to receive them. Okay, there is a congestion problem. Okay, right? Fast producer and slow receiver. If that is the case, there is a congestion. There is a mismatch in the speed of accessing the tokens and the generating the generating the tokens. So if that is the case, what happens is a lot of the compilation time will be wasted. Okay, so it will take more time for the compilation. Okay, so to avoid that, what they are proposing is like what they was proposed is, as and when the parser requests a token, it will send a request, as you can see here. So whenever parser requires a token, it will send a request. Okay, it will send a request to the lexical analyzer. Then lexical analyzer start identifying the the token from the source program. So whenever it finds one, then it will pass the token to parser. So this is how these two works. Okay, so as and when the parser requests a new token, it will send a request to the lexical analyzer. Upon getting the request, the lexical analyzer start trying to identify the lexemes or the tokens from the source program. Okay, right? So as you can see here, these two phases are somewhat they are interrelated. Hence why you can design them in a single pass. Okay, single pass. So that means you can write a main program. The main program is nothing but the parser program. Okay, within the parser program, as and when we require a token, okay, it will simply call the lexical analyzer function. Okay, the lexical analyzer function will start identifying the lexemes and return those lexemes to the main function, that is the parser function. Okay, so while designing, you can consider this also, but what we are doing here is we'll go for the independent approach, individual modules approach. Why? Because that will give you, it's a simpler design and it has more advantages. Okay, right? In the later phases, if you want to change the lexical analyzer phase or the parser phase, okay, if they're combined, it is very difficult for us to change the one module. Okay, you have to remove the entire module and you have to write a new module from the scratch. Okay, to avoid such drawbacks, what we'll do is we'll go for the simple design. In the simpler design, what we'll do is the lexical analyzer will be it is implemented separately and parser will be implemented separately, and then we'll provide this link. Okay, right? Since they are logically cohesive units. So we'll see that later, right? So in this particular class, what we are going to do is we are going to study the theory behind the lexical analyzer implementation. Okay, how to implement lexical analyzer. Okay, so these are the reasons why to separate. Okay, so if you separate lexical analysis from syntax analysis, it is easier, somewhat simpler design, and individually you can tune them, like you can optimize the modules, like you can optimize the lexical analyzer process separately, and you can optimize the syntax analyzer analysis process separately. And portability in the sense, this lexical analysis process can be ported to any machine, or the syntax analysis, if they are independent, if they are separated, if they are not interleaved, then they can be ported to anywhere, and you can add other modules to them. Okay, so that it can be worked for other languages also, right? And another reason is there are tools to implement lexical analyzers and parsers independently. Okay, so as I told you earlier, there are so many built-in tools, especially in Linux environment. We have tools like Lex and Yak. Okay, so Lex is the tool for generating the lexical analyzers, and Yak is the tool for generating the what you call that, parsers, right? So already tools are available, so hence why we go for the simpler design, independent design. Okay, so that is the reason behind this. Okay, otherwise we will be having only a single phase, both the combined phase. But in our compiler design, phases of compiler design that we have learned in the earlier class, there we have lexical analysis a separate process, syntax analysis separate process, right? So this is the reason behind that separation. Even though they are doing the correlated work, but we are separating them because of these advantages, right? So next, next thing, when we talk about lexical analysis, you need to know these three terms. Okay, you need to be familiar with these three terms. Okay, these three terms are very very. I mean, the important terminology with respect to lexical analysis process, but they're often confusing. Okay, almost. I mean, tokens, lexemes, and patterns, they're having similar definitions, but they're different. They're different. Okay, right? So let us see what is token. Okay, so tokens include keywords, operators, identifiers, constants, literal strings, punctuation symbols. Okay, so what I mean to say here is token is nothing but a class of symbols, we can say. Class of symbols. Okay, so token is the generalized name given to a set of strings. Say suppose, as you can see here, tokens include keywords. Okay, like if we take C programming language, C high level language, we'll be having somewhere around 32 keywords. So in C we have 32 keywords. Okay, all these 32 keywords will be considered as tokens. Okay, and the token class corresponding to them is keyword. Okay, keyword, right? Similarly, if you take operators, in operators we have different types of operators like arithmetic operators, logical operators, bitwise operators, conditional operators, relational operators. Like if you take arithmetic operators, plus, minus, multiplication symbol, division symbol, and modulus symbol. Okay, there are 5 fundamental operators, arithmetic operators. Okay, so this entire class, right? So this entire class is called operators token, a keywords token, identifiers token, constant token, literal strings token, punctuation symbols token. Okay, there are plenty of punctuation symbols like single quote, double quote, comma, full stop. These are all punctuation symbols, special symbols, right? So what I mean to say here is a token is a generalized term used to describe a set of strings with respect to the programming language under consideration. Like if you take C, in C the keywords token consisting of 32 strings like if, char, float, void. Okay, as you know, there are 32 keywords, no? Return, if, then, else, all these things, right? Now see the next one, that is lexeme. So lexeme is the word or the term usually used to refer a sequence of characters in the source program representing a token. Okay, say suppose, let me give you a small example here. I followed by n followed by t. I followed by n followed by t is a sequence of characters in the source program which is representing a token from the token class keywords. Int is a keyword, right? So what is lexeme here? Lexeme is the actual sequence of characters that are being identified from the source program in the lexical analysis process is called lexeme. Okay, right? A set of lexemes are called tokens. Okay, right? Set of lexemes means, I mean, the lexemes under keywords token class is different from the lexemes under operators token class. Okay, how do you get the difference? How do you know? whether it belongs to the operators token, token class, or keywords token class, or identifiers token class. So that is based on the pattern. Okay, right? So that is where the third term comes into picture. Okay, the pattern is a rule. So basically, it's a rule. Okay, the pattern is a rule describing a set of lexemes that can represent a particular token. That can represent a particular token. For example, let us consider this identifiers class, identifiers token. Identifier is basically it's a common name, it's a generalized name, okay, representing the variables. Okay, so this is token. Identifier is a token, but there is a pattern called letter followed by letter or digit, linear closure of letter or digit, that means asterisk, followed by delimiter, delim. Okay, in C, anything, any string which follows this particular pattern. Okay, this is what we call rule. So this is a rule now. Okay, so what this rule states, it says that anything which starts with a letter followed by one or more letter or digits followed by a delimiter is said to be an identifier. Okay, so this rule is nothing but it is often known as pattern. Okay, pattern. Okay, right? So all the variables, all the names which follows this particular pattern are said to be, there comes under the identifiers. There comes under the class, token class identifiers. Okay, so any string which follows this particular pattern, which naturally comes under that identifier category. Okay, right? So that is the I mean the relationship among these three, right? Token, lexeme, patterns. Pattern is nothing but a rule. Okay, all the lexemes which follows a particular rule or a particular pattern are said to be a token class. Token class, right? Okay, you got my point. So if you have any doubt up to now, you can ask. Otherwise, we'll proceed. Hello. Yeah. So the next we'll have something called attributes. Attributes provides additional information about tokens. Technically speaking, lexical analyzers usually provide a single attribute for token. Okay, might be pointer into a symbol table. Okay, attribute is nothing but the additional information corresponding to a particular token. For example, say suppose whenever the source program identifies a token called int, okay, in addition to the actual lexeme that is identified, it will also provide a number. Okay, so suppose int comma 60, where 60 is the number, okay, or the numeric value that is associated with the integer variable. Okay, right? So that information may be passed to the parser, right? So such things like attributes are nothing but the properties of a particular token. Like if you take keyword, its lexeme is nothing but its property, right? So all the 32 keywords are considered as keywords only. We don't know which particular lexeme we have identified. Okay, so suppose if you identified float FLOAT, then the FLOAT will be the attribute, the actual sequence, the actual lexeme, or the float value, the value of that particular keyword. Okay, or the variable. Okay, that is nothing but the attribute. So, how to identify the main task of the lexical analyzer is to identify the tokens. Okay, so the entire process is called tokenization. Okay, the main task of lexical analysis is tokenization. So for that, what it will do is it will use something called input buffering. Okay, so most lexical analyzers, they will use a buffer. Okay, for uh, for reading the input from the source program. Okay, often buffers are divided into two n character halves. Okay, so the entire buffer is it is divided into two halves. Okay, where n is a, it could be any number, that depends on the compiler design. Okay, the compiler designer, right? And we'll be using two pointers used to indicate start and end of lexeme. Okay, start and end of lexeme. Okay, if pointer walks past end of either half of the buffer, the other half of the buffer is reloaded. Okay, so once you're done with the half of the buffer, then the other half is going to hold the next input. Okay, so that is how we'll say. Like, so a sentinel character can be used to decrease number of checks necessary. Okay, you can use a counter variable where you can count the number of checks. Okay, so uh, right, so this is where now let's talk about the implementation of lexical analyzers. Okay, so how to implement this lexical analyzer process. Okay, so how to do that? It's pretty simple. All that you need to do is this is where the flat comes into picture, formal language and automata theory. If you look at the main task of the lexical analyzer, the main task is tokenization. Okay, it has to identify the tokens. Okay, what are tokens? Tokens are nothing but sequence of strings belongs to a particular class. Okay, sequence of strings which follows a particular pattern. Obviously, that belongs to some class. Okay, that is what we call token class. Okay, so our main task is to identify the tokens from the source program. Okay, so our main task is to identify the tokens from the source program. Okay, so for that, what we have to do, we need something called pattern recognizers, right? So what I mean to say here is we are trying to identify the patterns. Okay, so if you have a pattern recognizer, then that will come to our rescue, right? So our task is to identify the patterns. Okay, what is pattern? Pattern is nothing but a rule. Okay, all the strings which follows a particular rule are said to be they're patternized, or they belongs to a particular pattern, or they belongs to a particular class which follows a particular pattern. Okay, now our task is we need to uh, write an algorithm, or we need to build a machine such a way that it can identify all the patterns of that particular programming language. Okay, so that is where the flat or the theory of computation comes into picture. Okay, as you can see here, if you remember, there is something called formal languages in flat, right? So let me recall some of the terminology that you might have studied in your previous semester, but let me recall, rewind it again, right? So as you can see here, uh, let us start with alphabet. Okay, alphabet is nothing but, usually we denote with sigma, right? Alphabet is any finite set of symbols. Okay, any finite set of symbols. Okay, they may be ASCII symbols, or they may be binary alphabet, or a set of tokens. Okay, any finite set of symbols are said to be an alphabet. Okay. For example, let me give you this example. Sigma equals to 0, comma 1, comma 2. Okay. This is the trinary language. Okay, like we have binary language, 0 and 1 are the only two symbols in that particular language. In that particular language, like if you consider this alphabet, here we have three symbols, 0, comma 1, comma 2. So we have a finite set of symbols. Finite means countable set of symbols. Okay, countable number, right? So here we have three symbols. Okay, 0, 1, 2. Okay, now I can form strings by using these three symbols like this. Say I can do something like 1 followed by 2 followed by 0 followed by 1, or something like 1 2 2 2 followed by 0 followed by 1. These are all the strings, okay, which are using the same alphabet. Okay, right? So the alphabet is same. We are using the only those three symbols only, 0, 1, and 2, and we are getting some strings. Okay, right? So what is string here? String is nothing but a finite sequence of symbols. Finite sequence of symbols drawn from an alphabet. Okay, so this is a finite sequence of symbol drawn from this particular alphabet. This particular alphabet, right? Understood? I hope you understand this one, the example, right? Next, the next comes the long base. So this is what we call formal language. Formal language is nothing but a set of strings over a fixed alphabet. Set of strings over a fixed alphabet. Like if you take binary alphabet, 0, comma 1, then the long base denoted by this particular sigma is the set of all possible binary strings. The set of all possible binary strings. Okay, so hence we call it as a binary long base. Binary long base. For example, 0 followed by 1, single 0, or single 1, or epsilon. Okay, null string, right? Or 4 ones followed by 4 zeros, 4 ones followed by 3 zeros, 1 0 double 0 followed by 2 ones, or like that. Okay, so you can take any valid binary string that comes under the binary long base. Binary long base. Okay, so what is long base? Long base is nothing but a set of strings over a fixed alphabet. Set of strings over a fixed alphabet, right? So other terms relating to strings are prefix, suffix, substring, proper prefix, proper suffix. Okay, I think all these things you have learned in your MFCS and TOC class. Okay, these two are, I mean, these things are not that much uh, needed for our discussion. So I'm just skipping that. Right. So next comes the operations on languages. Okay, what we can do with the and what are all the operations that we can perform on languages. Okay, like these are some of the primitive operations that we can perform on languages. Like we can add two languages. That is what we call union, or we can do concatenation. Concatenation is something like we will take one string from one language, the other string from the other language, and we'll try to append them. I mean the second string is going to be appended with the first string. Okay, probably from different languages, different formal languages. Okay, I think you might have studied this linear closure in your flat. Linear closure is nothing but zero or more repetitions of the its preceding symbol. For example, let me give you that, 0 to the power of asterisk. Okay, some people are still, they're joining. 0 to the power of asterisk. Okay, this is what we call linear closure. Okay, So 0 to the power of star is nothing but 0 repetitions of 0, that is nothing but epsilon. Okay, 1 repetition of 0, you will get single 0. 2 repetitions of 0, 2 zeros. 3 repetitions, 3 zeros, and so on. Okay, right? And repetitions are infinite repetitions of 0. Okay, so this is what we call linear closure. Linear closure means 0 or more repetitions of a particular symbol or a particular expression is said to be linear closure. Okay, so then comes the positive closure. Positive closure is nothing but one or more repetition, one or more repetition. So the main difference between uh, linear closure and the positive closure is in linear closure we will be having null string also. In positive closure we are starting with this component, one repetitions of the preceding string. Okay, so this is positive closure. So if you combine positive closure with epsilon, you will get linear closure. Okay, then yeah, it's not scrolling down. So one or more repetitions, right? So, so let me clear all the lines here. Right. So the next comes the regular expressions. Okay. Now, what is the importance of regular expressions here? The regular expressions, like they will act as a specifiers. Okay. By using regular expressions, we can specify the uh, long ways. Okay, and we have studied a beautiful theory. Each and every, for every regular expression we can construct a machine called a finite state machine. Okay, which will recognize the long ways as denoted by the regular expressions. Okay, so that is the fundamental theory behind this lexical analysis. Okay, so what we are going to do here is we are going to study the pattern specifiers, and we are going to study the pattern recognizers. Pattern recognizers. Our regular expressions will act as pattern specifiers. For specifying our language patterns, we'll use regular expressions. For recognizing them, we'll construct machines. Okay, those are nothing but finite state machines. Finite state machines. If you recall, the flat